All right, so let's start by going over the first half of the lecture, volcanoes. Yes, it has nothing to do with the planet Vulcan. In fact, we're talking about the explodey boys that everybody likes to put in movies such as Dante's Peak. So let's start with the first question of what is a volcano? Is it merely the surface manifestation of the magmatic processes operating at depth? Is it a typical cone-shaped hill or mountain formed at a vent from which molten rock called magma or magmatic gases reach the Earth's surface and erupt? Is it a vent at the Earth's surface through which magma and associated gases erupt and also the cone built by such eruptions? Or is it a place on Earth of the globe where the temperature can achieve in rhythmic or permanent fashion a temperature much higher than that of the surrounding area, and the temperature difference can be over 1,000 degrees Celsius? Or is it a geologic environment that, at any scale, is characterized by three linked elements: magma, eruption, and edifice? It is sufficient that only one of these elements is proven as long as the others are inferred to exist, have existed, or have the potential to exist. Whichever one you think it is actually D, because they can be active or dormant, meaning that you're generally going to be having a temperature difference there that you can see with infrared in particular, but you can also tell by LiDAR data, which is cool. Who studies volcanoes? A person who studies volcanoes is a volcanologist, and the study of volcanoes is known as volcanology. There are different studies within volcanology, such as geochemistry, geophysics, seismology. There are people who actually study the movement of ash. There's geochronology and petrology and so much more. But a volcano is considered active because that's what everybody cares about, right? If it's active. If it's currently erupting, shows signs of unrest, such as ash is coming out, gases are coming out, there's earthquakes happening because magma is coming to the surface. If it has erupted in historic time, i.e. during the span of recorded history. And this is actually a very interesting point for activity, because recorded human history varies depending on where you are in the world. For the Greeks, it's more than 3,000 years. In the USA, it's less than 300 years. In Hawaii in particular, it's a little more than 200 years. Okay. And then if it's not active, but could become restless and erupt again, it is considered dormant. There are some volcanoes out there that we have considered to not even be working anymore or be extinct. Okay. Scientists don't actually like to use that word anymore, the extinct volcano. And that is because of problems like this, where we thought it was, but it wasn't. And one of the most recent happenings of this was Mount St. Helens. Mount St. Helens was thought to be a dead volcano, basically, extinct. And then it erupted. And a lot of people died. And it made scientists realize that there really isn't such thing as an extinct volcano. And so this is how we learned about volcanoes having essentially patterns. Maybe there are eruptions once every so many thousands of years that was never recorded, and so we think it's dead, but it's actually not. And we can tell this by dating the lavas or ash produced by its previous eruptions. Generally, volcanologists will determine a volcano is extinct if it has not erupted for at least 10,000 years and is not expected to erupt again in a comparable timescale in the future. So using this information, what do you think Yellowstone National Park is? Active, dormant, or extinct? If you immediately went, it's active, you are correct. Technically, the Yellowstone volcano, is an active volcanic source. Okay, the magma body underneath is active. It is still working. That is part of the reason why there are so many eruptions, or not eruptions. There are no eruptions at Yellowstone right now. It is part of the reason that there are a lot of earthquakes and why we have geysers there. It has hot gases escaping. It has hot springs, which are really nice. And these are all indicators of volcanic activity. It has erupted every 630,000 to 800,000 years, which has been dated, so we know there's a pattern. Thus, even though it hasn't erupted in the past 10,000 years, we know it will erupt again at some point. But due to scientific study, we know that it probably won't erupt in the near future. Why? Because we don't think there's enough magma underneath that could potentially make it to the surface. And we'll talk about magma in a little bit, but generally, magma isn't like this tea. It's not this like runny liquid that's just going to come out of the earth whenever it wants. No. And we'll talk about why in a bit when we actually get to the part where we talk about how lava forms and what magma actually is. But we have seen the caldera through seismic waves. We just don't know how much eruptible magma there is. Like I said, there could be little pockets of magma that's actually liquid enough to do anything, but it hasn't received a catalyst, or it's too small, there's not enough. Basically what's going on is there's activity, but nothing that would be considered world-altering or life-threatening, or the fact that there's going to be eruptions anytime soon. So let's talk about some fun facts. There have been 1,511 volcanoes in the last 10,000 years. There have been 5,350 eruptions in historical record. But this doesn't count the most recent eruptions that happened over the past couple of years, such as the ones that happened in Indonesia. Okay, we have had more. I believe this number was counted last in 2015. The biggest volcano is about 80,000 kilometers cubed, which is Mauna Loa in Hawaii. The tallest eruption was 6,887 meters, which was the, and I'm sorry for butchering this, the Ojos del Salado in Chile. The biggest eruption, with not just lava, was 2,800 kilometers cubed of material being eruption at Mount Toba in 74,000 in Indonesia. It's pretty cool. The first volcanologist was Pliny the Younger. Okay, so there's Pliny the Elder, there's Pliny the Younger. And Pliny the Younger actually stood on a boat and described the eruption of Pompeii in 79 AD. The amount of deaths caused by eruptions between 1600 and 1986 has been greater than 260,000. Within the last 15 years, we figured out how to track eruptions through remote sensors. And any deaths recorded before 1600 are considered uncertain. And contrary to popular belief, most people aren't killed by lava, but are killed by ash, lahars, pyroclastic density currents, or bombs. Yes. Volcanoes make bombs. They're essentially gigantic rocks that they throw out that could be partially molten. They could be something that fell in and then just got erupted out. And they're pretty big, like bigger than me, like bigger than your refrigerator sometimes. And they can crush you. Volcanoes have given more natural resources than death in the form of soil that we use to grow plants, minerals, and it's why you can plant some really good things around the base of a volcano. For example, in Italy, pretty much around the bases of volcanoes are all the wineries, and that's there for a reason. So let's review. What is necessary for a volcano? Magma. If there's no magma, there's no volcano. And magma is formed due to partial melting of the lithosphere, which then rises, forming basically the plumbing of a volcano, which are the dikes, the sills, the laccoliths. And what partial melting means is that you're not getting a whole bunch of rock melting at once, turning into liquid just like an ice cube does. Okay? You're not having an ice cube just melting. You're not having a rock just melt lava. No. What happens is you get these little tiny pieces of melt happening. So let's get a pen. You get pretty much like the edges of a rock starting to melt, and it forms these little droplets, and these droplets are then less dense than the solid rock around it, and so it rises and it comes together, and eventually you get enough magma to rise to the surface and make a volcano. Okay. So I know this is one of the answers in your study guide, so please make sure you write this down. Magma is formed due to partial melting of the lithosphere. Okay. Do not miss out on that. That's very important information that you need in order to fill out that question. Okay. So as I said, the edges of the rock or the boundaries start to melt. It comes together because it's less dense. It rises. And so then you get the separation of liquid and the gaseous phase of magma due to pre-existing fractures in the crust. Basically, there's all these cracks, and it's just like, oh, I can go this way. And basically what happens is, because a liquid it has to be really, really hot in order to melt. So because of this liquid being hotter than the rock around it, it's less dense. less dense material likes to rise like a balloon. 90% of magma never actually makes it to the surface. It actually ends up getting trapped in the crust somewhere. And that's how we get some of the really cool rocks that we like to make into countertops, i.e. granite. So to help you remember grain boundary melting, think of an ice cube. An ice cube just doesn't magically turn into a puddle of water. The edges of the ice cube get wet first as it starts to melt away, slowly shrinking and getting smaller. So the same thing happens with a rock. It'll melt along the edges and it'll slowly get smaller. Okay. What ends up tending to melt first due to the temperature that it melts at is actually what we call felsic material. And these are what make up a lot of our lighter rocks like what we see in here. Okay, like quartz. That felsic material is things like quartz, a lot of your micas, really cool things like that you all enjoy and you don't even realize it. But the addition of things like water makes the actual necessary temperature and pressure that the rock needs to be under in order to melt lessen. So when we have areas like subduction zones, you'll end up getting a cooler magma than a place like, let's say, Yellowstone National Park or Hawaii, where your magma is forming deep down and rising straight to the surface. And so here we see partial melting, you get mafic and felsic magma. And the part of the reason that you end up with felsic materials like quartz melting first is because the temperature that it takes to melt it is actually lower. So think of the difference between melting lead and melting iron. Lead is really easy, especially for those of you who have seen soldering before. If you haven't seen soldering, go watch a YouTube video of what soldering looks like. All you have to do is heat up, for example, a pipe to a certain temperature and the solder just melts right on. But iron doesn't melt like that. Iron, you have to heat it up to thousands of degrees. So think about it that way. Mafic is like iron, felsic, lead. All right. So what ends up happening is magma rises and it forms something called dikes and sills. Dikes are going to be your vertical up and down. Your sills are going to be your horizontal side-to-side movement. So basically what happens is your magma is not just going to go to the surface. It kind of gets stuck because maybe the crack goes this way, but then there's cracks going sideways, and that's easier. It's easier to go sideways, find another crack going up and go up that way. And so that's how you get like the network of dikes and sills going through, and you get the volcanic plumbing system. Magma ascension or magma rising is different for each type of volcano origin. At divergent boundaries or areas where the crust moves apart like this, you have decompression, which means that you're just having gas getting removed, and that's what's pushing it up. At convergent boundaries or subduction zones, the major driver is the addition of water, because the part that's getting subducted has been hydrated in the ocean. And so as that sinks, water gets added to the system, allowing for a cooler magma to form. At a hotspot or interplate volcano, again, like Hawaii, what's happening is it's so hot that it's actually just able to rise really, really fast. So to go over this, you have a sill, a dike, and a laccolith. Okay, and we see in the picture here, all three, right? So here's our dike, this part right here. We have our sill. Dikes can also end up going at an angle like this. And then we have our laccolith. Think of a laccolith as a really, really fat sill. Okay. A laccolith can cause deformities on the surface where it can cause the surface to make a hill type shape. If a conduit formed here, which is the part that brings it up to the volcano, we would get a volcano forming. But if we don't, then there is no volcano. And so laccoliths are really cool because if they're trapped under there and they cool and they harden, you get like this huge piece of granite. And a great example of a laccolith getting frozen is Yosemite National Park. Yosemite National Park. Sorry, it's spelled that way. So what kind of volcanism exists? You have interplate volcanism, which is also known as hotspot volcanism. Okay. It's usually seen as something called a hotspot, where you have essentially just magma rising to the surface. Ta-da! And it forms places like Yellowstone and Hawaii. They can occur in the ocean, and they can occur in the center of the crust. Let's pretend this is a continental piece. Okay, so we have continents. right? A hotspot happens in the middle of the continent. It does not happen at the edge. And that's part of what makes it a hotspot. Whereas if we have something like a subduction zone, where you have a piece going down under the continent, forming a volcano, that's different. That is now happening at the edge of the volcano. Okay? And that's where we get stuff like this. But a hotspot volcano, the hotspot itself stays put, which is really, really cool. A hotspot stays put. The continent keeps moving. Again, like we mentioned earlier, this is part of how we know that plate motion exists. And you can actually diagram and put on a map like we have here the path that these volcanoes have taken as the plates have moved, which is cool. So yeah, the Yellowstone hotspot or the Yellowstone volcano was not always in Yellowstone National Park. The path that it travels is actually known as the Snake River Plain, which is really cool. So there's a lot of different volcanic edifices, basically a lot of volcanic evidence along the Snake River Plain before it reaches Yellowstone National Park, which is really, really neat. All right, and then we have the Ring of Fire again, because we know. This indicates the different volcanoes forming along the edge of plates, okay, forming arc volcanism or subduction-related volcanism, okay? So whereas the Hawaiian hotspot and the Yellowstone hotspot are directly in the middle of a plate, you have all these other volcanoes along the edge, which are a result of subduction, okay? And it's known as arc volcanism. The Antilles Islands in the Caribbean are a result of this type of volcanism, which is really neat. So the next time anybody gets a chance to go on a cruise, if you choose to go on a cruise and you go to the Antilles, you'll actually see magma. You'll see eroded pieces where you can, especially in the older Antilles, you'll see eroded areas where you can actually see what once was underground. So you'll see cooled magma. You'll see lava flows, so you'll be able to actually see basalt. It's really cool. But when you get to the Ring of Fire, there is a lot of things that you hear, such as if one volcano goes off, all of them will go off. They're all tied together. So many volcanoes erupting on the Ring of Fire. We're doomed. Not true. Each volcano on the Ring of Fire is its own independent volcano. The reason we call it the Ring of Fire is because these volcanoes kind of form a ring-like structure because of how they formed, because we have subduction happening all along the edge of that plate, which happens to be the Pacific plate. Okay? So don't forget. So here we have, again, interplate, Hawaii, Yellowstone, subduction, which leads to island arcs and continental arcs. Japan is an example of an island arc where you have an oceanic crust going underneath another oceanic crust, forming a volcano. The Cascades are an example of a continental arc where you have oceanic crust going underneath continental crust instead. Remember that subducted crust has a lot of water in it, which allows a lower temperature to form this magma. So that plate that's going under is going to melt at a much lower temperature than the magma that we see at Hawaii, for example. So let's go over some examples of volcanic arcs, because you guys need to know this. The easiest ones to remember are the Cascades and Japan. But other ones involve the Antilles. You have the Andes Mountains in South America. You have the Aleutian Islands in in Alaska. And the Marianas, which, yes, has to do with the Marianas Trench. So since we talked about volcanic island arcs forming, Indonesia is a fantastic example. Indonesia is basically one giant chain of volcanoes that has formed the country. So there's a lot of volcanoes that are constantly erupting, and we hear a lot about them on the news. Sometimes it'll sound like the world's going to end for Indonesia because how many volcanic issues they're having, such as a ton of ash has come spewing out of Merapi, for example, or Toba is showing signs of unrest, Or let's think of another one. Krakatoa. Baby Krakatoa is starting to have unrest again. We might have another eruption. Oh no. Yes, Krakatoa, for those of you who know Krakatoa, it was a major eruption that essentially blew the island of Krakatoa apart. And in 2018, it rebuilt itself and had another massive eruption, which also blew itself apart again. And it's rebuilt itself since. So Krakatoa has been in the news a lot. You've probably heard of it. You may have watched a documentary about it in history class at some point in your life. But yeah, there's a lot that happens in Indonesia. So a lot of people like to go there and actually study. It's a big area. And then here we have the Cascade Range, which goes from Portland all the way down to, Washington all the way down to Northern California, ending with Lassen Peak and Lassen National Park, which, if you get a chance to go see it, I recommend it. The last eruption was in 1914, so it was actually pretty recent. Mount St. Helens being the most recent eruption in the Cascade Mountains. A friend of mine is actually checking out Medicine Lake volcano because of a lot of cool things that have happened there, which would help explain some of the things that happen in this boundary here, which is also really cool. So a lot of these have national or parks built up around them. If you get the chance to go out there and see them, I very much encourage it. It is really cool to see. All right, so now we're going to talk about different types of magma. You don't just get the same magma from every volcano. Remember, I mentioned some are hotter and some are cooler. And because of this hotter and cooler, we also have different makeups. We have different elements, different minerals in these magmas, which means some magmas are more explosive. Other magmas are more funny. It happens. Temperature of a magma directly affects how easily it can move. Viscosity is ease of mobility, or how much it will resist its flow. So the more viscous, the more sticky it is. Think of warm honey versus cold honey versus peanut butter. Basalt is going to be your warmer honey. Andesite is our middle, so it's going to be cold honey. And rhyolite is going to be our peanut butter mixture. A lot of times you'll have different types of peanut butter or rhyolite, some being a lot chunky, so think extra chunky peanut butter versus smooth peanut butter. The more sticky the magma is, the less likely it is to flow. And so I want you guys all to think about this. We've all seen a honey jar. We've seen the bubbles of air stuck in honey. And so I'm sure you can imagine what on earth could happen if I try to blow bubbles into cold honey. Well, that air's not really going to go much anywhere. And if it does manage to make it out, it's going to make my face all sticky. What about if I tried to blow bubbles in peanut butter? That probably wouldn't work out very well. You get a lot of bubbles under there and you might cause a peanut butter explosion, which I don't think would be very fun to clean up. Warm honey, though, if you blow bubbles into it, the air bubbles will come out pretty easily. So the stickier it is, the higher the chance it is to trap gas, and the higher the chance it is to explode. So how do you increase or decrease this viscosity? One way is heat. The hotter it is, the more fluid it will be, the less likely it will hold onto those gas bubbles. Another one is silica content. How much silica is in there? The more silica it has, the more sticky it is. Remember when we talked about in the beginning how lava or how magma forms? You tend to get your felsic material to melt first. Well, that felsic material has a lot of silica in it, which remember, silica is is quartz. Hands down, just plain old quartz silica. All right. So rhyolite is going to have a lot of the silica content. It's going to be very sticky. It's also going to be pretty cool. So it has a huge chance to be explosive. Your andesite or your middle one is going to kind of be in the middle. It can be explosive. It could not be explosive. And your basalt is your hottest. It's the most fluid. It has the lowest amount of silica. And it tends to just blow. You're not really going to have a lot of explosive basaltic volcanoes. And when there is one, it's pretty crazy. Well, what kind of volcanoes are there in the world? You have stratovolcanoes, which are also known as composite volcanoes, shield volcanoes, scoria or cinder cones, fissure volcanoes. And then on top of it, you could have a one-time eruption volcano, which is known as a monogenetic or a multi-eruption volcano, which is known as a polygenetic. But you don't really need to worry about that. You just need to worry about these guys. A scoria or cinder cone is essentially a cone of a volcano that is made up of the accumulation of volcanic fragments. And we're actually going to see this in a lab. You're going to see pictures of like blocks, bombs, lapilli, and ash. And that's what makes up the edge of this. So it's really crumbly. And when you try to walk up the side of these cones, it's kind of like trying to walk up sand. It's very difficult. It gets in your shoes. It sucks. But basically, this is like a sandhill, but made of like pieces of magma or lava as it's reached the surface, that as it gets exploded, it turns into these broken apart pieces and just lands there and sticks to itself and cools. Your slope tends to be pretty shallow because just like when you're piling up sand at the beach that isn't wet, it can only go up so high before it collapses on itself. Lapilli, which is part of what makes this up, is only between 64 and 2 millimeters in diameter, and ash tends to be less than 2 millimeters in diameter. But a bomb can be much bigger. It can be 64 millimeters, same thing with blocks. They can get bigger than a refrigerator. Okay, so they're pretty dangerous when they're flying out. A lot of times they'll have this huge crater at the top. They can have lava flows that happen, but a lot of times, again, their entire cone system is made up of this exploding parts, the exploding lava, which is what we call pyroclasts. A scoria cone is usually 95% of the time a single eruption, but sometimes you get polygenetic or multiple eruptions. But generally, it's going to have only one eruption, and that one eruption is what's going to build it up. They tend to form very quickly. An example of this is actually SP Crater, which we see here, which is located north of Flagstaff, Arizona. If you get the chance to ever go out to Flagstaff, go ahead and check out the San Francisco volcanic field. It's really, really cool. There are 4 main stages. You have the initial phreatomagmatic stage, where it's like just exploding out bits. A lot of times this involves water to be involved, so it causes it to really explode really fast. You'll have the main cone growth. You have late cone growth due to some explosions, which we'll get to later, but this particular one is known as the strombolian explosion, where you have just this big bubble of gas that comes out and it causes a spray. And then once it gets too heavy, it starts to collapse. Our next type is a shield volcano. One of the most well-known shield volcanoes that we know of is Mauna Loa in Hawaii. They generally form from intraplate volcanism, i.e. hot spots. They tend to start out when they're underneath the water as a seamount or underwater volcano and grow into islands, like the island of Hawaii. The shield itself is an accumulation of just lava flows over and over again around a fixed vent. Their slope is very shallow. It's less than 20 degrees. And the summit is going to be the caldera of the volcano. And this is Rangitoto in New Zealand. And we can see right here, it's a pretty shallow slope that we have going on. And it kind of looks like a shield that's sideways. But generally shield volcanoes, like I said, they do have a central conduit, but they can also have rift zones or fractures. And these are weak zones on the volcano where magma can just kind of like shoot up through. And since there's a lot of pressure here, it can cause something called a lava fountain, which is actually pretty cool. When you look at videos of just generic YouTube videos of eruptions in Hawaii, you'll often see a clip of something like this in there, which is known as a lava fountain. And it has actually gotten the name of Hawaiian-style eruptions because of this. So a strata/composite volcano, which is the same exact thing, is a sort of volcano that tends to form at convergent plate boundaries or subduction zones. Okay. Their cone is the accumulation of volcanic products. This is your iconic pointy volcano. It's kind of like a weird layer cake where you're going to have lava, ash, pyroclasts. Lava, ash, and pyroclasts all mixed together. And because you have lava involved with these pyroclasts, they're going to stick together, again, forming a really weird layer cake and giving you that iconic cone. There are many types. You have the simple cone, you have shield-like, you have clusters like this one, or three sisters where you have multiple edifices together. You have twins, you have ridges where essentially the volcano gets long like this, and that's actually due to the vent moving. And then you have this is generally the type of volcano that we associate with super explosive eruptions with lots of pyroclasts, and we tend to see this one in movies a lot, or whenever you watch Fantasia, for example, Fantasia where the dinosaurs are dying. This is the volcano that you have erupting in the background. So here's a nice little table with a summary of the different types of volcanoes and some examples for each of them. If you want to look it over, you can. So now let's talk about volcano anatomy. Again, the plumbing of a volcano, like the dikes and the sills, which tend to be what we call the magma chamber, the conduit, which is how your magma will travel to the vent of the volcano, becoming lava. The vent is where magma will exit the volcano, and the crater is the circular depression at the top. If you have a caldera, that means your crater is greater than 1 kilometer in diameter. When you have parasitic cones, that means that the side of your volcano, you're having an explosion off the side. Think the end of The Lord of the Rings and the Three Towers after Frodo has finally gotten the ring, well, really, Smeagol has gotten the ring into the lava, and all of a sudden lava starts erupting out of the side of the volcano. That's a flank eruption. A fumarole is kind of like a flank eruption, but it's all gas, which is pretty cool. So here I have an example of a dike. This is from the Museum of Natural History. Not the Museum of Natural History. I'm so sorry. This is from the Smithsonian Museum of Natural History. And this is called a granodiorite. It's something that you'll find from, let's say, a Laccolith, where it has cooled and a dike has gone through it, which is pretty neat. And this is called a cross-cutting dike. Anyway, so in a volcano, there's not really a magma chamber. Like, everybody thinks there's this big ball of magma underneath a volcano. That's not really true. What you're going to have is a collection of dikes and sills, maybe a laccolith. And you can have a large intrusion, like I said, laccolith, batholith, that can get exposed later over time. But these sills and dikes are a pretty neat network that end up happening, and they can actually displace the surface. So where you have a smooth surface, if you have like a laccolith or a batholith, it can actually cause an inflation of the surface like this. And maybe one day that will have a break. Maybe finally it makes it to the surface, and you'll have a volcano form from that. And then we have lava domes. Lava domes are an intrusion of magma on a flank or in the crater of a volcano, so it's a little different. And it domes up like this. And when it collapses, like the magma finally breaks out forming lava, it can actually cause a huge debris flow in addition to there being a lava flow, which is really dangerous. A batholith is different from a laccolith just because of how big it is. A laccolith is like an inflated sill. A batholith is like a gigantic laccolith. Okay, and so whereas a batholith just intrudes between sedimentary rocks around it, a batholith can be hundreds of kilometers long. Okay, and then you get things like stocks, which can be hundreds of kilometers cubed in just stuff that's inside of it, which is, they get big. And so when they get shown, because maybe we have enough erosion that we can finally see it, you get these huge chunks of things like this, diorite, or granite just coming out. And we're like, wow, look at that mountain. And it turns out, no, it's not a mountain. It was, that was a batholith. So we get a lot of cool things underneath a volcano or underneath a volcanic field. But remember, 90% of magma never makes it to the surface. So we have a lot more laccoliths, staccoliths, batholiths, sills and dikes that are just sitting underneath the surface that will never make it. Can you imagine if it was 90% of lava made it to the surface instead? We would have a pretty wild world. So here we have an example. Here's a dike that has been surfaced. Okay, so dikes, even though they're going vertical, can be pretty long. They're usually no wider than maybe 2-3 feet wide though. And then over here we have a sill. So sills are horizontal and they can get pretty thick. They can get as thick as I am tall. And then here is a laccolith after it's been exposed. And then Mount Ellen is actually a stock. So it actually goes super duper duper deep. And these are part of the Henry Mountains in Utah, which is pretty cool. And that's the first half of the volcano lecture. I'll see you guys again in part 2 for Volcanoes B. Thank you very much for sitting in on our lecture today, and I hope you enjoyed it and that you were able to follow along. Remember, post any and all questions that you have in the Discord, not the Discord, the discussion post for this lecture, and I'll make sure to get back to you on any questions that you guys have. Have a good night.